Welcome back. This is an Aleks homework video on estimating a phase transition temperature from standard thermodynamic data. So if you're trying to find a melting point or a boiling point, I probably would just look up the boiling point or the freezing point. That's probably what I would do. But if you want to, you can use the thermodynamic data that's in the Aleks data table to do it. Okay, because what they're teaching you is that everything is related. And how is it related? That's what you're trying to learn. Okay, so first of all, it's boiling. And so you have to recall what a boiling point is. A boiling point is the temperature at which the energy inside the liquid becoming a gas is exactly equal to the atmospheric pressure that's pushing that and condensing it back into a liquid. So you've got the condensing and the vaporization at equilibrium. So it's an equilibrium point. So if you remember your delta G, or your Gibbs free energy, the energy that's actually able to do work with, that energy if you were to have something that's higher than the boiling point, then all of it is going to go to vapor. It's spontaneous going to vapor. If you have something less than the boiling point, it stays as a liquid. But if it's at the boiling point, then your delta G is going to equal 0. And that's what we're going to use today. All right, that's the trick. If you know that at the boiling point, delta G is equal to 0, you can simply take your normal formula. Delta G equals your change in enthalpy minus the Kelvin temperature times the change in entropy. Change it back, get a temperature. Now this is your Kelvin temperature, and then realize that your G is 0. So really, your temperature is going to be your enthalpy change, your total energy change, divided by the randomness or your entropy change. And since we've got the same material, you're simply going to take it from a liquid to a gas. You can look up the entropy of formation of a liquid of benzene and a gas of benzene. You can look up the entropy, formation entropy of the liquid benzene and the gaseous benzene, and that's where we're going to go. We're going to basically take the difference and then divide that out and find that temperature in Celsius, and then that's going to be your boiling point. So you're simply going to take the enthalpy of formation, your heat of formation of the gas, and then subtract the heat of formation of your liquid. And you're going to do the same for the entropy. So let's do the enthalpy first. I simply looked up these in the data table and subtracted it. This is kilojoules per mole. Entropy is kilojoules per mole. To be careful, entropy is not kilojoules per mole. Entropy is joules over Kelvin moles. Okay, so I'm really lazy. I don't write my units very much. If you don't write your units, you're going to get trapped. You're going to multiply wrong numbers. If you recognize that your units are not the same, you can convert those units at the end really simply. So this teaches me to always write my units down. But in any case, I've got an entropy change here, and I'm going to divide them. Now, before I divide them, I can't divide kilojoules by joules and get Kelvin, so I need to change them both either to kilojoules or both to joules. I guess it doesn't matter. It'll all cancel out anyway. So I change them both here to joules, and then since I've got the entropy as Kelvin moles on the bottom, when everything cancels, I'll end up with Kelvin. So I changed Kelvin into Celsius and then went up to, rounded it to the nearest degree and got 80 degrees. Okay, so I hope that helps.